Hi, this is a video introduction of my work titled Direct Parameterization of Pythagorean Triples. Several years ago, I began to think about this interesting property of a parameterization of Pythagorean triples. Coming back to this problem from time to time over the years, I was able to find more and more examples that have this interesting property, and this paper is to introduce those examples. Let me begin with the abstract of the paper. If the two axes of symmetry of a quadratic form in two variables have integer coefficients, the reflection across the axes defines a group action on the primitive solutions of the Diophantine equation defined by the quadratic form. Here's an example of a quadratic form. In fact, only the left-hand side is called a quadratic form. And by putting a constant on the right-hand side, we generate a Cartesian equation that is closely related to this quadratic form. The ellipse in blue color is the graph of the Cartesian equation, and the two lines are the axes of symmetry. We assume in this work that the Cartesian equations of the two lines are given by integer coefficients. Let me explain the Diophantine equation defined by the quadratic form. Suppose you have a rational solution for this equation. Then by clearing the denominators, which are positive integers, we generate an equation of the following form. Here we can see z as a common denominator of the earlier rational solutions. This equation in three variables is a Diophantine equation defined by the quadratic form. Each term of this Diophantine equation is degree 2, and this will allow us to easily find a solution with no common factors. For example, x equal to 9, y equal to 21, and z equal to 24 is a solution, and they have a common factor of 3. After canceling 3, we have x equal to 3, y equal to 7, and z equal to 8. And they remain to be a solution. Especially this new solution has no more common factor other than a positive 1 or a negative 1. And we call it a primitive solution. Now, if we choose a rational solution on the blue ellipse, it corresponds to a unique primitive solution with a positive z value. And the points obtained by reflecting them across the axis of symmetry generate additional primitive solutions. This uses the fact that axes of symmetry are defined over the rationals. For this example, reflection is simply changing the x and y coordinates and their signs. So in this paper, we introduce quadratic forms with rational axis of symmetry that admit a single set of polynomials, which parameterize their primitive solutions up to reflections. The standard method of parameterizing rational solutions is to use projection, and it generates a parameterization of the Diophantine equation as well. It turns out that for some equations, the parameterization never directly generates a primitive solution. For example, it may generate 40, 84, and 68, but it may never generate its primitive version 10, 21, and 17. However, it may generate its reflected version 21, 10, and 17. If the axis of symmetry is not y equals x and y equals negative x, the reflected versions are not simply exchanging the coordinates. In this work, we introduce equations that admit a polynomial parameterization that reaches all the primitive solutions up to reflections. The important part is parameterizing the primitive solutions. Indeed, there are examples of equations for which the standard parameterization never generates a primitive solution and any of its reflected versions. Let us introduce the theorem. Let k of xy be a binary quadratic form ax squared plus bxy plus cy squared with integer coefficients, such that the absolute value of its discriminant is an odd prime number d. Suppose that the associated conic section k of uv equal to 1 has a rational axis of symmetry, and let alpha beta and negative comma alpha in integer coordinates be direction vectors of this axis where the GCD of alpha and beta is equal to 1. I guess we understood all the terms of this part, and I'll say a bit more about the prime condition on the discriminant in a second. Let Q be 1 or an odd prime, different from D, and suppose that the Diophantine equation k of xy equal to qz squared in xyz has a solution x naught, y naught, 1, if q is not equal to 1, and alpha squared plus beta squared is not congruent to 0 mod q, then the polynomials of two variables, which is described at the bottom of the screen, make a parameterization of the symmetry classes of a primitive solutions of the Diophantine equation with restrictions kxm plus kyn not congruent to 0 mod d and mod q if q is not equal to 1. And this holds if q is equal to 1 as well. Here, kx and ky are the values of a partial derivative at the point xy, x naught, commas, y naught. I believe that the condition on the discriminant and the prime q is necessary, and in the future work, we plan to prove that a direct parameterization does not exist for this case, meaning that if a discriminant is not prime and q is not prime. Later, I bumped into Professor Westerstein's work on the parameterization of SL2Z, which is cited below, and using many more variables, we could remove the restriction on the congruence conditions. That is, the primitive solution of our equations can be parameterized by a single set of polynomials in 98 variables, up to reflections. Recall that I got interested in this problem from staring at the standard parameterization of Pythagorean triples. From a geometric point of view, the task is to find all triangles that have integer side lengths and have an angle of measure 90 degrees. In general, we may consider any angle for which the cosine value is rational, and the task is to parameterize the primitive solutions of the law of cosine equation shown on the left side of this slide. If the fixed angle is 60 degrees, the solutions of the equations are related to the Eisenstein integers, which are generated by the third root of unity in the complex plane, and for that reason, the solutions are called Eisenstein triples. Our main result is for quadratic forms, but the original task of this work was to find more angles that admit a direct parameterization of the solutions of this cosine equation. Inspired by the Gaussian integers and the Eisenstein integers, my first approach toward finding more angles used a unique factorization property of the ring of integers of the quadratic imaginary fields. It was conjectured by Gauss that there are only finitely many such fields, and in the early 1900s, the finiteness was proved, and the complete list, which is shown in the slide, was determined in the mid-1900s. For example, the law of cosine equation with discriminant negative 163 is 41x squared minus 81xy plus 41y squared equal to 41z squared. And the parameterization will reach all primitive congruent triangles, meaning that a triangle with the sides 3, 4, 5 is identified with the one with the sides 4, 5, 3. Honoring Gauss's conjecture, I named these primitive triples Gaussian triples. I think I forgot to show the theorem in the parameterization while I'm explaining this slide. So here is the parameterization for that equation corresponding to the discriminant negative 163. However, the projection method generates many more angles, such angles, and it seems that there are infinitely many such angles. The infinitude of such angles remains conjectural since it is equivalent to the infinitude of prime pairs Qn for Q minus 1. So Q is an odd prime, and 4Q minus 1 must be also prime. This is a conjectural. This is remained as a conjecture according to the celebrated result of Green and Tau. I suspect whether the property of a direct parameterization is canonical, meaning that it does not depend on coordinates. For example, if we have this law of cosine equation, can there be a parameterization different from the standard one such that it is direct? One of our future work is to show that this particular equation does not admit a single set of polynomials that directly parameterizes the congruent primitive triangles with angle theta. As you can see, this angle came from one of these angles in the famous 3, 4, 5 right triangle. This part is not included in the paper, but I find the following graph interesting, and I would like to coin the term Eisenstein Graph for this one. The angle in the lower left corner is 60 degrees, and the nodes on both sides mark the points whose distance to the lower left vertex is an integer. Two nodes from different sides are connected if the distance is integer valued. So this graph represents the collection of all primitive Eisenstein triples. For example, the tiny triangle at the lower left corner is an equilateral primitive triangle with side length 1. If we remove the lower left vertex, it forms an infinite bipartite graph, and we may ask ourselves standard graph theory questions on that bipartite graph. For example, if we truncate both sides to length x, what is the size of a maximum matching as an asymptotic function of x? What is the size of the longest path as an asymptotic function of x? We may also ask the number of edges in terms of x and the average values of the lengths of the edges in terms of x. This concludes the video instruction of my work. Thank you for watching.